All right, so let's get started here. So thanks for the introduction, Yuval. So this will be a talk on lower bounds for differentially private RAMs. As Casper introduced in his last talk, it's related to ORAMs, but a weaker version of security. And this is joint work with Pino Persiano at Google University. He's also at the University of Salerno. I hope this works. Good. All right, so this might be an introduction again, but let's start off from scratch. So what is a privacy-preserving storage protocol, essentially? So you have the client on the right and the server on the left, and the client wants to privately outsource a large amount of data to a server. So the typical way you could do this, or the most naive approach, is simply to do client-side encryption. So the client holds some private key and only outsources encrypted data. But as you all already know, when you do stuff like naive, so let's say this client wants to download index I, and it does a naive retrieval of index I. Even though these blocks are encrypted, the server gets to see information, just literally index I was downloaded. It might not seem right so bad off the bat, but what happens is, let's suppose you do this, this eavesdropping over a year, you get pretty complex statistics. So things like, index 15 was the most frequently downloaded, index 2 was never downloaded, and you get like a lot of information. It's been shown in practical situations such as encrypted search, where this sort of leakage can actually be used to reverse engineer the data set or information about the data set, especially if you have like a priori knowledge. All right, so this essentially leads us to the idea where we want to essentially somehow obfuscate or hide these patterns of access to encrypted data. And this is essentially so an ideal scenario, what you want is the client wants index I. Now it does a sequence of more complex accesses. So this could include things like moving blocks around, downloading different blocks, stuff like that, just an ORAM, as I guess that's what you guys already know as. And it gets block I, and the server essentially doesn't know what was the requested index. It essentially obfuscates this value. And you can view this as a single, I've done this singles access. Casper has represented this as an algorithm, but they're the same. And this is literally what's been called oblivious RAM, which was introduced by Goldreich and Ostrovsky in the 90s, or even I think by Goldreich in the 80s. But all right, let's go through the definition a little more carefully, because we're going to be modifying the definition for our paper, or for this work. So what does an oblivious RAM do? It takes these two access patterns. The first one is like the one on the top is accessing block 5, block 27, block 13, et cetera, and the bottom one's doing the same thing. They're doing the same number of accesses, but they can be to completely different indices. And what an ORAM does essentially is it takes the sequence and compiles it. And what do I mean by compile? I mean, back to this more complex sequence of accesses, essentially. Right? This could involve moving blocks, downloading extra blocks, et cetera, stuff like that. And the typical definition essentially says that the compiled sequences that have to be generated by these ORAMs, they must be indistinguishable. And this could be done in terms of both statistical and computational security, where the adversary is either bounded or not. All right, so what we're considering in this work is a weaker notion of differential privacy, is a weaker notion of ORAM called differentially private RAMs. So what was happening before was that you had, the ORAM had to take two sequences that could be vastly different and had to compile them in a way that was indistinguishable. So what we consider by differentially private RAMs is this weaker notion of, you have these two sequences of the same length again, but they differ in exactly and at most one location. So here, the bolded 213 and 692 are the only ones that are different. And we want to do the same thing. We want to say essentially if we take two sequences that differ at one location, we can compile them using a differentially private RAM. And what we don't want is indistinguishability anymore. We want this, general notion of differential privacy for things like composability. So, if you haven't seen this formula before, essentially it's done for composability. You can get security parameters for like sequences that differ at k locations. The epsilon and delta multiplied by k. That's just the simplest notion of composability. But essentially, this allows us to compose and get a smooth sense of a security across many different patterns. But it's clearly weaker, right? Much weaker. It's only trying to hide patterns that differ at one location. And okay, some people might ask, what's the motivation of such a definition, right? So this is more folklore. This is not something more formal, but the way I think about it is something like, consider the day, your normal day when you're like, accessing the web. What the differentially private RAM essentially does is, I have a typical pattern of how I access data. In the morning I check the weather, I check my email, at the end of the day I check my path home, stuff like that. What this can essentially do is it hides that one abnormal access, or it can attempt to, right? Some point, I don't know, I'm running out of money, I need to search for something, I'm a bankruptcy lawyer or something like that. That's what it tries to hide, right? This one weird notion of access. And this is what it's essentially trying to do, right? And it's a natural notion. I don't care about you leaking the entire, statistics about the entire pattern, but rather just, just hide the one abnormal one, or give me, some sense of, you wouldn't know for sure whether I did something or not, right? This is what this is attempting to try to, define. Test how?
I agree, it's natural, but still I want to ask you, you said before for regular RAM that there are like practical works that exploited information. Are those practical works use sequences that are closed? Or I don't know these works.
Yeah, no, so I believe they're a little different in that they really require a priori knowledge of the data set, it's like a dictionary, or it's like the English corpus, or something like along those lines, right? And that's how they reverse engineer. I mean, there are other examples. For example, if you just did the naive retrievals, you could do things like, at 8 a.m., every day I access one block, and that's clearly my password manager, or something like that, right? Those kind of things. So you're right, I don't know what the security implications of this definition is, and it's a good thing that we don't need to find out because of our result, essentially. Okay, so I just note that computational differential privacy, we're considering A to be, a bounded PPT algorithm, right? So this is computational differential privacy. Okay, so I sort of spoiled the result now, but an interesting question now is, differentially private RAM is a weakening of ORAM, and in terms of privacy, much weaker. It seems right off the bat, much weaker, right? We're saying, hey, hide two patterns that differ at exactly one location, and we don't even want negligible difference anymore. We want this ratio of epsilon and delta, where epsilon's constant, maybe delta is some negligible function. So can we construct differentially private RAMs that are faster than ORAMs? And I can tell you, Pino and I spent a long time trying to do this, and it didn't work out well for us for this reason. It's okay, but I spoiled it again. So before we do that, let me go back to the ORAM bounds. There's been a long work of ORAMs starting from the 80s with Goldreich Strachty that gave polylog overhead, and eventually it got down to logn with this optorama by Asherov and all. And the lower bounds has also been, it's been a long time coming, but the work was very, there was a work in the 90s, and then Casper and Jesper came in and essentially solved it. But essentially there are two omega logn lower bounds that show, the Goldreich Strachty was statistically secure with all these assumptions that Casper described before, and then this paper, the best paper of What a Crypto, actually removed all these assumptions essentially. All right, so here's our contributions, which I've spoiled already, but essentially what we show is that for any natural parameters of differential privacy that you would ever consider, epsilon being constant and delta being any constant less than 1, actually. We do 1/3, but you can get anything less than 1. Typically, again, delta should be negligible. Essentially, we show that differentially private RAMs require omega logn overhead. In other words, an ORAM would be the best differentially private RAM from an asymptotic point of view. So we don't have to answer this question anymore, what does it mean in terms of leakage? And we get some stronger bounds, actually. So the previous Larson-Nielsen result shows that essentially the addition, so the max of the read and write operations have to be omega log n. But it doesn't rule out things like, hey, the reads could be log n, but the writes could be constant, or vice versa. And in this work, what we show is this actually can't happen. We show these very strong trade-offs where, for example, if the writes use sublogarithmic overhead, the reads spike up to superlogarithmic, and vice versa. So essentially what the best thing is literally is this optorama, which has log n for both. And in other words, what we say is DPRAM is not asymptotically faster than ORAM for typical differentially private parameters, and even ones that are actually much weaker. All right, so let me describe quickly the model for which we prove it. Yes?
So do we have positive result about this asymmetric case? Because it could still be interesting. So in a setting where you have fewer read and more writes.
I think we rule it out, actually, in some sense, right? Or you want to say, can we do something where there's super, I don't know, that'd be.
Super expensive writes because I don't do many.
Sure, it's possible. I actually don't know. I don't think there's any work on this. Maybe the original Goldreich square root ORAM has something like this. I'm not sure. That could be. But. OK, so how do we prove these lower bounds? We use something called the cell probe model. So again, we have the client on the right, the server on the left. And what we consider is the server's storage is actually split up into these things called cells, memory cells, which are W bits, like Casper had done before. I'm being a little less formal, but essentially the idea is what happens is in a cell probe data structure, or in the oblivious cell probe data structure, the client will essentially probe a cell. And that's the only unit of cost. That's the only thing we charge in this model. So what we essentially say is computation is free. In fact, the data structure is allowed to do infinite amounts of computation. And what it means essentially is that by using this very weak cost model for lower bounds, we obviously apply to stronger lower bounds that also cost for computation in a reasonable manner. All right, so I guess we'll see the information transfer technique again. Again, I'll quickly go over I'll go over quickly the Larson-Nielsen lower bound. But I wanted to essentially tell you guys why it won't apply for differentially private RAMs. And I think Casper showed it a little bit. I'll get into a little more detail here. But again, quickly recall that this Larson-Nielsen lower bound uses the information transfer from the Petrascu domain paper from '06. What it does essentially is, okay, I think Casper's tree was that way. Mine just rotated. Essentially, you have a tree with exactly n leaves, and you assign an operation to each leaf. And what is this hard sequence? As Casper said, he had done it for the stack. I'm doing it for the ORAM, or for the array, which is essentially, let's say, write 0, read 0, right? This is a very easy access pattern, essentially. But the key point we're going to do is that it's going to be very different. It's going to be very close to all of these nastier, worse sequences that require a lot of overhead. And when you combine them together, you'll get the lower bound, right? This is what Casper had done. And like I said, it's easy to handle. No, it's oblivious because it's to be oblivious for more complex sequences. So okay, like I said, we assign each of these operations to a leaf. And each of these operations are actually implemented with cell reads and cell writes. So this is what Casper called probes, but I just pretend to see. I'm saying it's a cell read, it's cell writes. So we can actually replace this write 0 to the array with these cell reads and cell writes. And the idea essentially is, let's suppose cell 15 was read in this operation. And then the last time it was written, the last time it was overwritten was in that operation. And what we essentially do is we assign this cell to the lowest common ancestor. This is another way of viewing the information transfer technique which Casper presented. And from a high level, what you can actually show is that, so there's 15 here, right? Let's say you do this for all the operations, for every cell read and write, right? Every adjacent cell read and cell write to the same cell. And what you can essentially show is that the probes assigned to a specific node are all the information that can be transferred from this top subtree of this node rooted at the subtree rooted at the red node. All the cells assigned to that specific node is exactly the amount of information that can be transferred from the top subtree to the bottom subtree. So in other words, the answers to these essentially the answers to these operations, if they use information from operations that were inserted in the upper subtree, it has to have been assigned to that cell, essentially. And to see why this is true, you can just look at other cells. For example, if you look at that one, well, remember how we defined assigning cells. Essentially, these cells are read in the top subtree as well, right? So they actually can't be used in the answers of the bottom subtree of the one rooted at the red. And similarly here, what happens is, well, you read the cell, but long after you have to give the answers for the operations in the bottom red subtree. And essentially, those are also useless. So long story short, all the cells assigned to this red subtree are the only ones that can be used there. And this is what Casper had said as well. And what happens is now, for each subtree, we do this hard distribution. What we're going to do is in the top subtree, we're going to write random blocks to different indices, and we're going to read those identical blocks as well. So you can think of this as maximizing the information transfer for this specific subtree. So this will maximize the number of probes that have to be assigned to the red node. And essentially this is the exact same argument that Casper had done, but if you have a subtree with 2L leaves, you have to essentially assign L times B over W probes to the subtree root. Just because you need to essentially transfer L times B bits. So if each cell has W bits, you need L times B over W probes. And then what happens is essentially an adversary can actually count the number of cell probes assigned to each node in the tree. So what essentially means is that you really need to assign a lot of probes. So whatever the worst case is for each subtree, you need to assign that many probes to each node. Otherwise, the adversary can tell the difference. Okay, so now that's the high-level point of view. I just reviewed what Casper had said, and now I tell you guys, now you guys want to know, why does this not work for differentially private RAM lower bounds? So the idea is the following, essentially. If you look at this, how the hard distribution is built, they really differ quite often. So they differ very much. For example, in this subtree, if you have 2L leaves, you really need to change all 2L operations, right? Okay, that's not a very strong argument. Maybe there's some way I can interlude the operations in such a way that maybe they don't have to change so much, but okay, just recall that, remember, like the differential private guarantees are very different than oblivious guarantees in that they exponentially decrease. If you have epsilon equals constant, they exponentially decrease, right? So by the time you get to like log n, you have no guarantees of security anymore. So this is why it's essentially too weak. And the idea is, let's suppose you change a single operation. Just change one operation, which is what differential privacy is trying to argue, or maybe a constant number, right? Let's say I change this read 0 to read 1. How many nodes in the information transfer tree can I actually affect? Well, it's just log n, right? It's just all of these green ones, essentially, all of its parents. And from this, you can quickly see that it doesn't seem like you could ever do this, right? Even if you try to nest the operations in a way that are close together. Each one can only change log n things, and that's not enough for us to change the lower bound. All right, so how do we do this? We use this chronogram technique by Friedman and Sachs, which is actually older than the information transfer technique. So what is it? Okay, so what I'm going to do here is I'm going to present a simple log n over log n lower bound, and I'll tell you the ideas of how to get back the log n factor a little later. All right, so what do? The hard sequence is a little different now. The hard sequence is, it's going to be writing n random blocks to literally just be n indices. You know, write a random block to the first index, the second index, all the way to the nth index. And all I'm going to do is read from the 0th index. And again, this looks trivial, right? If we assume, if I never wrote to the 0th block, it should be easy to return whatever it was initially assigned as, it should be returned. But again, what we're going to do is we're going to show that this is very similar to a bunch of more complex, nastier sequences, and to hide this fact, you have to do this. And just this little spoiler, what we're going to be doing is making sure we only change the read operation. So again, remember differential privacy, we can only change one operation. Okay, so what we do is, you guys have seen this already, what we're going to do is we divide the write operations into these epochs of geometrically decreasing size by some factor beta. And just to note carefully, we actually, just for convenience of the sizes, we number the epochs in reverse order. So the largest epoch occurs first, and the smallest epoch occurs at the end. All right, so the idea essentially is, okay, remember this. We have the cell pro model. The server has all these cells. And what we're going to do is, by the time we get to the read operation, so let's say we executed all of the write operations, and we've seen, okay, in each write operation, which cell was overwritten, right? Which contents of cells were overwritten. And using this, we can actually number each cell according to the last epoch that overwrote a cell. So what does this mean? This top left cell here, the one number 5, it means an operation in epoch 5 was the last operation to overwrite the contents of that cell before the read operation and across, right? So essentially now the question, okay, so let's say so going back to this, let's suppose, essentially what we're going to do is now is we're going to analyze where can information about a specific epoch ever be stored. So the idea is, let's say we fix an epoch, for concreteness, let's say it's epoch 5. And exactly the question now is, what happened in epoch 5 is we wrote beta to the 5 operations of random blocks to disjoint indices, right? And these are literally random bit strings. And where is the information about these bit strings stored? Well, okay, start off the simplest one. Of course, if you overwrote a cell in epoch 5, you had those bit strings. That information can be stored in these cells. And of course, it can be all future operations as well, right? So like I said, I numbered the epochs in reverse. So all epochs that happen in the future, that were overwritten by an epoch in the future, can also contain information about epoch 5. So these are two things in all the future epochs. Okay, so then what we quickly note is that now you might ask, and I think Casper already said this, but why are these epochs geometrically decreasing? I haven't told you yet, I just told you that we did it like this. And essentially the trick is if you pick, because they're geometrically decreasing, the operations in the future are not as there are not as many operations in the future as there are in epoch I. So if this beta is greater than 2, you have at most beta I minus 1 updates, right? And what you're trying to say is essentially if you pick beta to be large enough, these epochs, the operations in the future don't have enough time to encode a lot of information about epoch I, right? Let's suppose this is like 1 over poly log n factor of the number of writes here, right? Because they all have the same, expected running time, there's just, these future epochs just don't have enough time to write information about epoch 5, or a meaningful amount of information. It can only write like a 1 over poly log n factor, for example. So So essentially this. So what we're saying is that, hey, these future epochs, because we did this geometric decay of epoch, oh, yes?
Maybe I'm missing this, but are you also accounting for the fact that information will be encoded in the choice of which cells you know?
So yes, we do. I haven't gone to the details of that, but yes, when you, it depends. The simpler one, you don't need to do that, but for the more complicated version where we get rid of the log n factor, we really have to be careful about that. So yes, you're exactly right in that. You can actually encode information in there and you have to account for it in the, it's a much more subtle issue. Essentially, how we actually prove these is like Casper was saying, we use a compression argument and show that we compress too little information. And you're exactly right that you have to also account for the fact that which cells you probe also contain information, and you have to include that in the compression argument. So you have to, whatever information you're able to answer has to overcome this as well. Where was I? Okay, I was saying, yeah, the future epochs don't contain much information. And finally, there's also this client memory issue, but let's suppose it's just small. All right, let's suppose for convenience, it just holds a key that's independent of the data set. All right, so let's suppose now we're going to pick a, I'm going to do a read. I'm going to look at a specific access sequence now, where I define read x, where x is going to be essentially, so I look at epoch I, and index x is chosen uniformly at random from all of the b to the I overwritten indices in epoch I. Right? So what I'm essentially saying is, okay, hey, each of these epochs are overriding disjoint blocks. My read, I'm just going to pick one epoch, and I'm just going to randomly read a uniformly random intelligent block from the one that's overwritten from this epoch. And now what I essentially try to convey now is the fact that you must read like omega b blocks if each of these blocks contain b bits. You must read omega b bits from last overwritten from epoch I. So from the cells that were last written from epoch I. So those are the ones that were numbered by 5. And essentially, we just did the argument literally. Client memory is too small. Cells last overwritten in future epochs, they don't hold significant information about epoch I. So essentially, what you're trying to do is you show that this thing has to read many cells that were last overwritten by epoch I. And now, how you piece these together essentially is you do this access pattern for literally all of the epochs. So this read x epoch 1 to epoch k, it'll be uniformly chosen, and because of this differential privacy thing, essentially the adversary shouldn't be able to count and see how many cells did you probe from each of these last epochs overwritten. Yes?
This question to your model. When you say that two sequences are neighboring, like they differ in the read, what if two write operations write some different data?
Right, so you have to actually be more careful. You have to actually do this through probabilistic methods. You can't just, so they're actually distributions. You're actually considering many distributions of different access sequences, and they all differ by one location. And because of, if you look at how the differential privacy works, so it's not as simple. Like for the ORAM lower bounds, what essentially is done, you can just argue straight away that it's done. There's one more step of like making sure you see the distributions of the patterns and making sure they're the same and stuff like that. But you're right, that's a point that we have to handle, but it's more of a subtle issue. Right, so this is how we do this. And now note that we only change the read operation. All the writes stay the same, we're only changing one operation, so differential privacy is still strong. And yeah, this must be true for all epochs, just for the same idea that Casper described for ORAM, which we've done before. Okay, so like we said, okay, this beta, what does this beta actually have to be? The beta actually has to be a lot larger than you'd expect. It can't be constant because of, essentially it has to be linear in the size of the write time, because otherwise you have to make sure that these future epochs can't write too much information about the previous epoch, right? So to do this in a naive fashion, you have to make this beta factor be this TW times W squared. And essentially this means it peaks at a log n over log n lower bound if you do the math properly. I haven't shown it, but what I promised to you guys is the log n lower bound, right? So I'll describe the main idea here. Essentially the idea is, what you're going to do is in this previous lower bound, what I described essentially was a sequence where I fixed the epochs ahead of time. So I told you, hey, there's n write operations followed by exactly read operation. And what it turns out is what we're playing is actually a game between an adversarial data structure and ourselves, which is the lower bound, the good guys, right? And we have to handle all of these data structures, including these really adversarial ones. And the idea is that you lose this log n factor because the adversarial data structure, it knows the structure of the epochs. It knows, hey, this epoch ends here, this epoch begins here, stuff like that. And what it can literally do, it can really try to do the following, which is the future epochs all ignore their answers, literally ignore all their write operations, and just attack a specific epoch, for example, epoch I, right? And all these future ones attack this epoch and say, I'm going to only try to process information about epoch I. And in this case, you can quickly see that this proof technique would actually, it just peaks there at that point because of this adversarial data structure. So to get around it, what we essentially do is when we generate our access pattern, we say is, we're going to generate, let's say, a 5n sequence of write operations, and somewhere between, the nth to the 5nth write operation, somewhere in there, we're going to embed the query operation uniformly at random. And then when we embed it uniformly at random, then we generate the epoch sequence. And because we switch the qualifier, essentially the adversarial data structure can no longer figure out, hey, which epoch is where, it can't attack a specific epoch, and we eventually show that the best you can do is essentially attack all the epochs simultaneously, and allows us to get this beta, we can make beta constant. If you want more details, it makes the proof a lot more complicated actually than the one here, because it turns out that you have to actually start encoding the cell probes, the exact cells that are being done as information, stuff like that as well. But if you want, you could take a look at the paper. It's a much more difficult topic. And I also promised you these stronger trade-offs. So it turns out once you start randomizing query locations and randomizing the epoch operation, the epochs, you can actually change how the epochs are built. So right now, the way I described it, the epoch decay geometrically, right? And what the idea is, if let's say, for example, you knew, let's say you're doing order log n writes, right? Let's say you're doing a very small number of writes. What you can actually now do is construct your epochs in a way that the future epochs can actually be larger. Why? Because they have much less time to do write operations, right? So if you change the epoch structure, you can create more epochs. And now when you do this read lower bound, you can essentially have super logarithmic number of epochs to do the read operations. Then vice versa you can do something similar also for the vice versa trade-off. And that's it. And if you're interested, since this is a lower bound workshop, here are several other lower bound works from our group. There's one that appeared at Pods just last week, actually. So most of these lower bounds, what we're doing is essentially saying, hey, we have a specific privacy we want to hit this privacy guarantee. What's the best runtime you can do? What if you flip the question and said, hey, I want to hit a very small overhead data structure that's private. What's the best privacy I can gain? And we essentially show in this that if you use this differential private thing, you can get epsilon equals theta log n. But I caution that it's a weaker lower bound and that it goes back to the balls and bins, Goldreich-Ostrovsky, statistical security, et cetera, stuff like that. The second work Casper just described in his previous talk. And this third one, what we essentially show is now we can actually, so in these ORAM and differentially private RAM lower bounds, we're considering smooth, almost what we call smooth leakage. How would we apply these kind of techniques to things like encrypted search or encrypted multi-maps? And Pino will describe more of that in the next session and how to use these techniques over there. That's it. So, okay, that's a good point. So I think Casper had written at some point these, what were they called, passive storage systems. So if you consider a passive storage system, which is normal ORAMs, all they're doing is literally, hey, request this or download it. And in that case, these runtime lower bounds become exactly communication. But you can actually view these as just runtime lower bounds. If you allow the server to do arbitrary computation, it could theoretically, do FHE on all the data, compute the result, and just give back one answer. Not unless you assume a passive server. These are all running time lower bounds, or like storage versus running time lower bounds. Yes?
So, like the Larson-Nielsen lower bound, right? Because it's oblivious RAM, then you can transfer the fact that you have a lot of queries for one bad distribution to like any input, right? To any input sequence. So for this differentially private RAMs, it's a bit challenging. Because like the first group that you show, right, there you're showing that you have like one specific hard distribution, but like it's possibly difficult to spread this to
Exactly,
everything.
yeah.
So the second distribution that you have for the
chronograph.
Can you actually say that like then it applies to most distributions, or it's still just like there is one worst case thing?
So actually it's the opposite, right? If you think about it, what we're trying to prove is, for differential private RAM, we're trying to prove that we're actually restricting our hard sequences to a much smaller set. So actually what happens is, what we're showing is that there exists a ball of hard sequences that are very similar, and that they all together combined, give these really bad overheads. So if you're asking, do they apply to like typical? Are you trying to ask if they apply to typical access patterns? I don't know. In fact, I would believe it's the opposite. The ORAM lower bounds would give you, because they're much more spread out and they're much more natural in the sense they apply everywhere, they might be better.
So that was exactly my concern, because you could still hope for like somewhat efficient differentially private RAM, right? But for most input sequences, you have sub-logarithmic overhead, and then there are just these like very bad input solutions where you convert this.
Right. So that could be true. I caution the fact that these lower bounds, essentially what you could do is literally ignore all the like you could just accumulate enough write operations, ignore all the read operations if they're like the same amount, and then just apply the chronogram technique again, right? If you ignore a constant factor number of queries, the bound still holds. So what you would maybe want to do is say, let me remove the read operation, right? And then you get to static lower bound, static data structure oblivious lower bounds, which are very scary, because they've been shown by this Weiss and Wick's work, which show that they're connected to locally decodable codes and or sorting circuits, both of which are very scary. Yep. Oh, yes.
You talked about even sort of more restricted notions of neighboring access patterns, like if it's not just that you swap one read for a write, but like you have to swap a read for another read, it's kind of.
So exactly, our bounds hold for that. Our bounds actually hold for that. In fact, I haven't said this, but if you look at our distributions, right, the hard sequences are only changing reads to reads. So there's.
Reads to nearby memory.
Oh, okay. So in that case, no, we don't consider that.
Is your sense that the lower bound should still hold a problem?
Actually, yeah, that's true. I forgot. We actually have a work on this in some sense where we show that you can actually define this you can define differential privacy in a different way called like L1 differential privacy, where not only is one operation different, but that one operation is different in literally one location, and we actually have constant overhead constructions for that. And also, I guess I didn't mention this here, but our lower bounds actually don't use any obliviousness for write operations. You can assume the write operations are actually completely insecure, because we're only changing the read operation.